Hey friends, welcome back to our YouTube channel Physics Zone. Today we will move ahead in our chapter of laws of motion. Today we will discuss horse and cart problem. So let's start. So this is the diagram with the help of which we will understand horse and cart problem. Okay, this is the cart and this is here horse, and these are all the forces which are acting on this horse and cart. The weight of cart is let W1 and its reaction force will be R1. Okay, here is the horse and the force due to weight of horse is W2 and its reaction will be R2. Okay, here F, this F is the reaction friction force that ground exerts on the feet of horse, and this R is the reaction of that friction force, and this R can be resolved into two components, R sin theta and R cos theta. When the angle with the ground of the reaction force is theta. Okay, now we can say the friction force, this friction force should be less than this r cos theta component. Only then the horse can move forward. Okay, here if r cos theta component is greater than this friction force, only then will the horse will be able to move forward. Okay, let's discuss again. This is the cart, its weight is W1 and its reaction force is R1. It is exerting a tension T and backward also T tension. Okay, here is the horse and its weight is W2 and its reaction force is R2. Okay, our friction force is exerted on the feet of a horse, that is F. Its reaction force is R. R is resolved into two components, R cos theta and R sin theta. Okay, now R cos theta is the component that is helping the horse to move forward, and the F is the friction force that is keeping it in forward direction, that is not supporting it to move forward. Okay, now when will the horse will able to move forward? Only when the r cos theta component will be greater than the friction force. Okay, so this is the horse and cart problem. Okay, now we will discuss apparent weight of a man in a lift or elevator. Okay, so now we will discuss apparent weight of a man in a lift or elevator. Okay, now this is the condition when the accelerator is at rest position, and this is the position when the accelerator is moving for upward. Okay, now when the accelerator is at rest position, means elevator or lift is at rest position, then the mg will be balanced by the reaction force r, means the acceleration of the person in the elevator will be zero because the accelerator or the elevator is at a position of rest. Okay, so net force will be zero. Acceleration is zero. We know from second law of motion, F is equal to ma, we have acceleration 0, so net force exerting on the person will be 0. Okay, so from here we can say exerting force or any external force is 0. Okay, so R will be totally balanced by mc. Okay, this is the case when the accelerator is at position of rest. That let's discuss when the accelerator is moving upward with the acceleration a. Okay, now the elevator is moving in upward direction. Acceleration is in upward direction. Accelerator is moving in upward direction. It means there is a net resultant force that is applying in upward direction. Okay, means there should be some force that is exerting in upward direction. Let's say F is the force that is the finally resultant resultant force that is exerting in upward direction. That's why the lift is moving in upward direction. Okay, so from here we can say the force that is uh, making this lift to move upward is the F, that will be equal to, it means F is the resultant of the R1 this and mg, means and the lift is moving in upward direction. So from here we can say R1 will be more than mg, this R1 will be more than mg. Okay, so from here we can write F is equal to R1 minus mg. Okay, so from here we can find out our reaction force R1 will be equal to F plus mc. Okay, here R1 is equal to m. Here F is the force. F can be written as F is equal to ma. So at the place of this F we can write ma plus mg. Okay, so R1 is equal to m into a plus g. Okay, so from here when the lift is moving in upward direction, we can say its reaction force will be R1 is equal to m into a plus g. Okay, and one thing we can see from here is that the lift will move upward only when R1 is greater than mg. Okay, so this was the case of the lift when it is moving in upward direction, means it is accelerating in upward direction. Okay, now we can see another case when the accelerator is moving in downward direction. Okay, so let's discuss that. So now this is the case when the accelerator is at rest, and this is the case when the accelerator is moving in downward direction. Okay, means the lift is accelerating in downward direction. Okay, so the accelerator is moving downward, it means the resultant force of the R1 and mc is exerting in downward direction. Let's have this F is acting in downward direction, that's why the lift is moving in downward direction. Okay, so from here we can say mg is greater than R1, only then the lift can move in downward direction. I hope you are getting me. Look, Here F will be equal to mc minus r1. Okay, so F, from here we can write r1 equal to mc minus f, r1 equal to mc minus f can be written as ma. So from here r1 will be equal to m into c minus a. Okay, so this is the case when the accelerator or elevator is moving in downward direction with an acceleration a. Okay, so from here we can say the accelerator will move in downward direction only when mg is greater than r1. Okay, mg is greater than r1. This is the condition when the accelerator will move in downward direction. Okay, look at here. When the lift was in a condition of rest, its mass was mg. That was experienced by lift or the human that is present in the lift. Okay, but now its mass is mc minus ma, that is experienced by the man that is present in the lift. Okay, so from here we can say when the accelerator is moving in downward direction, then the weight that is experienced by the man that is in the lift is less than the actual one. Okay, that's the case you have felt during you were in accelerator. Okay, another case here we can discuss is when acceleration is equal to g. If we make acceleration is equal to z, what may be the condition then? Then r1 will equal to 0. Okay, that's the condition when the man in the lift will experience 0 mass. It will be the condition of massless. Okay, this will be the condition of weightlessness. Okay, another case we can discuss, if acceleration is greater than g, what will happen then? If the acceleration is greater than g, that's the condition when r1 will be negative. Okay, means the weight that is man experiencing in downward direction is much greater than the reaction force. Sorry, the reaction force is much greater than the weight of the man that is in the lift. Okay, so is in this case the man can get injury because when lift is moving in downward direction, but the man will experience a force in upward direction, the man may move up than the roof of the lift. That may cause a great injury to the man. Okay, so this was the case of the forces acceleration when it is moving in downward direction. Okay, so the next topic we will discuss here is the principle of conservation of linear momentum. Okay, So let's consider we have one body here. Its momentum, its mass is m and it is moving with velocity v1. Its mass is m1. Okay, here is another body that is moving with velocity v2 and its mass is m2. After moving some distance, they may collide with each other. Okay, its momentum, we know momentum is mass into velocity, so its momentum will be, let's say, p1, and its momentum, let's say, p2. Okay, now after collision, what will be their momentum? Let's its momentum is p1 dash and its momentum is p2 dash. Okay, now according to principle of conservation of linear momentum, we can say the sum of the momentum that was in initial condition. In initial condition, the momentum was of first body it was p1 and of second body it was p2. According to linear momentum, their sum will be equal to the momentum that is after the collision. After the collision, the momentum of first body is p1 dash and of second body is p2 dash. Nothing but it is the conservation of linear momentum. So it was all about principle of conservation of linear momentum. So thank you for watching my video and have a nice day.